Thank you. You won't be able to mess a two-letter last name. So today I'd like to talk about our case study in analyzing the security and privacy of tire pressure monitoring system used in automobile. This is joint work done by my students at University of South Carolina, as well as the WinLab Rutgers team. So, well, you all have cars, and you probably have already seen there's increasing number of wireless devices has been put into the car, and especially hook up to this CAN bus. So CAN stands for Control Area Network, which can control the brake and all window, all those stuff. Now, if you go to a dealer and finance your car, your dealer might install this web-based vehicle immobilizer to your car. Once you stop paying, they can send a command through a pager network and disable your car, and then they can possess it. And your insurance company might also tells you, we can lower your premium if you allow us to install these MyRate devices, which you will hook into the OBD, the onboard diagnostic port. And this thing's actually worked through cell phone network. It basically reports your driving behavior, like acceleration and duration of traveling time and etc. And in last year, the Geneva Auto Show, there's some system called iChange. Basically, you can use iPhone to control your car. There's many more, and this is actually the car itself. So there's actually many more. Those wireless sensor network will be put on into the car. Now, the first mandatory in-car sensing network is actually the TPMS, the tire pressure monitoring system. Somehow it got chopped off. So the TPMS actually will monitor the air pressure inside each tire in real time, and then will alert the driver if any of them is underinflated. Well, this, of course, an inappropriate inflated car can cause security and safety problem. For instance, this crash plane is actually partially caused by the underinflated tire. And if you see in the middle, an improperly inflated tire can reduce the lifetime of your tire and also reduce the gas mileage. So go home, check your tire pressure, and make sure they're correct. Anyway, so in light of those advantages, the National Highway Transportation Safety Administrator has mandates that all cars sold or manufactured after 2008 have to be equipped with this TPMS. Now, there's two types of TPMS. One is indirect one, where I use the ABS, anti-lock braking system, which is not as accurate as the direct one, which actually use the wireless sensors. So in this project, we actually look at the direct TPMS, since virtually all cars use this type. Now, you may think, what's the big deal of this tire pressure? What can we do about it? Now, let me just show you a few misuse. So, for instance, if you're driving your car down the road and your car is constantly sending out those messages and there's sensor ID in it, so if someone deploys some sniffer around the road, or maybe just in a few spots, and they can record where have you been and when you've been there. Well, I don't think Tiger Woods will like to hear that hotel will actually have this system installed. Anyway, the other use is that you can actually, maybe we can try to, oops, the wrong direction. Maybe we can to inject the forged message and make your TPMS system to believe that the tire pressure is low. Well, you may ask again, what's the big deal? The driver will at most stop and check the tire pressure. Well, actually, there's a report in Italy. There's this highway robbery, and the robber will typically put a barrier on the highway. Now, imagine we have this high-tech robber. They can save that energy in cutting down the tree or moving the rocks. So, well, motivated by the trend, there's increasing number of in-car sensors going to be there, and they're going to be those type of risk. And actually, if you think about beyond those risks, if in the future there's more sensor deployed in car, and if the sensing data is actually used to control car, so for instance, if the tire pressure is used to assist the ABS or the stability control, then spoofing attack will become far more serious. And you may already know that early this year, another team in UW and UCSD, they actually show that if you hook a computer into this CAN bus, you can kind of disable the brake and lock the window. Now, if we marry the wireless technology with the CAN bus, I don't even need to tell you what's going to happen. Okay, so motivated by all those risks and trends, so we want to know how likely we can reverse engineer, just find out all the communication protocol detail and how likely is to track a car, and especially what is the range. There's actually many work like hacking the RFID, try to figure out, they actually show that the RFID can give you pretty large distance of the eavesdropping rate. Now with the car, it has a metal body, so we'll ask, will that metal body be able to block the signal completely? And will we able to actually send out the faked message? Because the antenna of the TPMS is typically under this wheel arch shell. And finally, we are also interested in what can we do to protect the TPMS communication. So let me start by tell you what we found out of those marketing material online. So a typical TPMS system, this is the architecture. You will have tire pressure sensor. Actually, I have one in hand. It's operated in battery, and it's actually installed in each wheel. This is actually the valve stem. And we also have a few antenna, which will pick out a signal and then send to this ECU, the electronic control unit. ECU will do some simple processing. For instance, it will drop the packet coming from neighboring car, will do some temperature compensation. And finally, we have the dash panel, and you will see what's the real tire pressure right now. Not real, let me be careful. It shows you the tire pressure, it bleeds, and also there's a warning light. In terms of communication, for each sensor, it actually have a sensor ID printed on the packet. So before the TPMS can work, typically the dealership, the technician has to manually input the sensor ID as long as with the sensor location into the ECU, so it will work correctly. Now, there's two types of communication happen inside the TPMS. The first is from the sensor to the ECU. It will report the sensing data periodically. And the other is actually from ECU. We'll send out a sensor, an activation signal to the sensor to wake it up at the frequency band of 125 kilohertz. Now, interestingly, the market materials say that we will put the sensor into sleep as often as it can. So the sensor will be activated when the car is traveling at a speed higher than 40 kilometers or 25 miles per hour. But later we find out actually many cars, their sensor will keep sending out message even the car engine is shut down. Well, we know what people always try to do. Security through obscurity, well, yeah, it always works, so that's why they hide the protocol details. Anyway, so in the first step, we try to figure out how can we turn the signal that's actually transmitted into air into something meaningful, basically the sensor ID, the pressure reading. To find that out, we need to find the modulation scheme and the encoding scheme, and also figure out whether the message has been encrypted. So this is the set of the equipment we use. We choose two types of sensors. Well, to avoid legal issue, let me just call them A and B. They are just, let me just say they're used in the most popular car in US. And we also have this ATAC VT55. This is actually a tool used in the dealership to do diagnosis and also to input the sensor ID into the TPMS unit. And to capture the signal, we use this Agilent vector signal analyzer. This is a piece of expensive equipment, and it's very powerful. It can capture signal starting from DC all the way to 6 gigahertz. And at the beginning, we use this device, but later on, we use the software-defined radio. So now, the difference between regular radio and software-defined radio is that a typical Wi-Fi car, once you buy it as a Wi-Fi, it is Wi-Fi. With software-defined, you can program it, make it as a cell phone receiver, transmitter, or the Wi-Fi car, and do all those fun things. And in particular, we use this hardware called USRP. I'm pretty sure many of you actually use it. And so it consists of a motherboard and also a few daughter boards. So it depends on which frequency you're gonna capture data, you have to pick the matching daughter board. Okay, so let me quickly go through the reverse engineer step. The first thing, capture the packet transmitted. So we use the ATAC to send out the activation signal, and the sensor will respond at 315 megahertz. Now we use either the VSA or the USRP to capture the signal. This is actually how the signal looks like in the time domain. So the green thing is the real part of the signal. The signal is typically a complex value. And the blue line is actually the envelope of the signal, or amplitude. So if you're staring at this, you can pretty much figure out what type of modulation scheme it probably is. To further confirm, we plot the signal into the frequency domain. Now, in this domain, you will see that actually there's only one clean spike, meaning that the modulation scheme is ASK, amplitude shifting keying. So you use a high amplitude to encode 1 and low amplitude for 0. Now, again, if you're staring at this thing, again, you can figure out the modulation scheme. Can anyone guess? It's actually Manchester. So you will see the widest, this square is actually 2 times of the narrowest one. So that's a typical Manchester. We actually spend like less than a day to figure out those details. And also, some are part of the packet format, like the sensor ID, then spend a few more days just to figure out all the detail, the checksum, and everything. So in the end, well, it's not a surprise that reverse engineer is possible. And also, there's no encryption, no surprise. And the funny thing is that with a car, it only has 4 sensors, and it has a sensor ID, either 28 bits or 32 bits. Now, what does this mean? If we do a birthday attack kind of calculation, so it will tell you if you want to have 2 cars have the same ID, and with the probability more than 1%, then you have to have 10 raised to the power to 15 cars operate in one region, which is much larger than 250 million cars is registered right now in the US and possibly in the future. So come back to the first misuse. So using this ID, you can pretty much identify each car. But also, of course, it depends on how they allocate the sensor ID. Now, the second question regarding whether we can track car is the range of eavesdropping. As I mentioned, the car body might be a strong shielding shell that prevent the IF to propagate. So in order to study that, we actually build a live eavesdropper. We use similar equipment as the reverse engineer part, except we stop using this expensive equipment and rely on the USRP only. And later on, we also buy a cheap low noise amplifier. And so here is actually the flow chart of this live eavesdropper. We use GNU Radio. It's an open source software, and it has provides you with many signal processing packets. It actually, you can think of this as the software part of the software-defined radio system, and this thing is the hardware part. So we use this script called USRP, so it basically will record whatever is transmitted in air, then output into the file. Well, if we just use this, then immediately we run into a problem, because if we are sampling at 4 megahertz, in each second you get 8 megabytes. And for 10 seconds, for 10 minutes, and if you want to eavesdrop longer, you probably don't want to do that. I don't even know how to, what is the unit of that. So what we did is actually we pipe the data collect and build this packet detector and only record data, only record the message. And then ideally, you feed this message into a modulation classifier, because some car are actually using the frequency shifting key. So actually, one of the sensors, we studied using FSK, the other using ASK. So once you decode this, the message at this stage, you will find the bit string. And well, ideally, if you want to do a massive reverse engineer, you will build this format classifier again to figure out what is the correct sensor ID temperature. Now, in our system, since we know exactly which type of sensor we use, so we actually didn't implement the classifier. So anyway, this is the system. Now, I'm going to show you a movie and show how we do the live eavesdropping. You will see that there will be a student standing close to the car, holding the ATAG thing, and keep clicking so it can activate the sensor, so we don't have to wait there for a long time before the sensor sends out. And this is actually the screen snapshot. So we place an USRP further down away, and let me just click it. So in this window, you will see the sensor ID, and this is actually the packet, and this is the zoomed in the packet. So if you matching what's showed here and here, this is the sensor ID. And then the student will come closer, will show you what's displayed on these ATAG devices. And this is actually matches with what we captured on the screen. Okay, so now we build the eavesdropping system, and then we like to find out what is the range. Again, we actually parked our car, and then we moved the USRP along this yellow line. And in the first set of experiment, we only used USRP and a cheap antenna. So this is actually the received signal strength, and this is distance. So you see, we got the distance at like 10 meters. And well, 10 meters is not a big deal, right? So we think, okay, let's put a low noise amplifier. It's actually this size. It gives you 20 dB gain, and immediately we can boost the range to 40 meters. Well, of course, you can do all those fancy stuff to increase the eavesdropping range. You can do the high gain antenna, antenna array, and all those fun things. Okay, so that the experiment you just see is actually you have to line everything perfectly. But if you think about the car tracking scenario, typically you have a, let's say, eavesdropper on the roadside, and the car gonna drive parallel to the curb. So we kind of try to use this experiment to emulate what's gonna going on. And to read this plot, we play the USRP at the origin, and we drive our car parallel to this x-axis. And then we drive for multiple lines, and then we plot the contour of the received signal strength. So if your car is inside this colored region, then the eavesdropper will be able to extract your sensor ID. Once your car is outside, then it cannot. So let's say the widest range here is 9 meters, which means pretty much you can place an eavesdropper on the curb, while if there's only one lane, then you pretty much can capture the sensor ID. Well, we also tried it in highway. I only report we tried it in 70 miles per hour because this is the highest speed limit in that highway. Well, you know the reason, okay. Anyway, so come back to the possibility of tracking. If we are only doing a passive tracking, so then it will be pretty difficult. So since the car will only report one packet every 60 or 90 seconds according to the regulation. And our eavesdropping range, the biggest is 9 meters. You can do a simple calculation. Then you find out in order to track like 60 miles per hour car, kilometers per hour car, then you have to have 110 sniffer. Although our system only costs probably $1,500 still, you don't want to do that. Well, okay, so then we look at what else can we do. We have this activation signal. So what we can do is we let a transmitter send out the activation signal when the car is approaching. Down the road, we place a sniffer, and then we will no longer be bound by the one packet per 60-second constraint. the only thing you want to be careful is how you can do the timing. So here we use USIP and 2 daughter board to capture the blue line is actually the activation signal, and also capture the green packet coming from the sensors. So you will see that the gap between you start to send this activation signal until the point you receive the first sensor data is approximately 500 milliseconds. So do some calculation, you know how you're going to place it well. Okay, so you may say, what's the big deal? We heard those car tracking a lot. We can do the camera. Like there's those license plate capture camera. They're actually in many places. So let me just point out differences. One difference, with the TPMS, you can hide where the sniffer is because it doesn't require line of sight. With camera, you have to install this camera in some visible place. If you are motivated enough or paranoid enough, you can find where those camera is and take a detour. Okay, so now that's the car tracking. I also mentioned that another misuse is the spoofing attack. So we want to know what's the range of the spoofing attack and whether the ECU have done some like input checking. Will the ECU actually find out there's some malicious packet sending in and then block it? First we use similar equipment, try to do the spoofing. Now, in order to send out the forged message, we have to be able to send at 315 megahertz. At the time of our experiment, actually there's no data board will transmit at that time. At that frequency they can receive. We actually use a TVX used for receiving TV signal. So in order to deal with, we use actually a device called frequency mixer, so it's this size. We actually use 2 data board, which works on 900 megahertz, and then by generating tone using 1 data board and generating data with other one and do it like a subtract, and then we managed to send at 350 megahertz. Well, it's actually pretty scary because you don't even need to have the right radio front end. You can still launch this attack. So anyway, this is the spoofing systems flow block. So starting from you get the sensor ID and sensor type from the eavesdropper. And then you can write a packet generator, basically do some modulation and encoding and then prepare the data. And we let the USIP to play that data out and then to send it out. So we tested our spoofing in 2 devices. The first is the dealer use tool, the ATAC tool. So we're thinking, okay, what kind of sensor ID we want to create, which no sensor probably will use, and it will also be accepted by the dealer's ATAC machine. Can you think of any ID? Because it will show up in hex. You can use the letter from A to F. So here's what we come up with. And so this, once we see that beef, we are pretty happy. Okay, now it's time to go to on the roadside and check our cars. So we actually use the left. I don't need to tell the details. So one of the tire of my car and my student prepared this packet. And I'm going to show you that what happened once Ish sitting on the roadside and start to send out this forged message. First, you will see that immediately after he started spoofing, you will see the 0 PSI and also the low pressure warning. And then about 6 seconds later, the car's general warning lights will turn on, tell you to check your tire pressure. Through all the time, the tire was perfectly fine. So in the end, we know that, okay, there's basically no authentication implemented in ECU. There's no input validation. Because we find later that every time when we send out a spoofed message, the ECU actually will try to probe the sensor. So the sensor will send back like 8 messages saying, I'm fine, I'm fine, I'm fine. But in spite of this 8 good message, as long as you have one kind of spoof message, it will mask those 8 messages. And we check the range. We just use a cheap antenna. The range can be like 38 meters. And also, we tried the inter-vehicle spoofing, so we basically drive on the highway. Again, this is just some speed we tried. I didn't tell you the highest speed I drove. So, okay, actually, then we are curious if you notice in the movie, actually, right before the car computer turned on, the tire pressure actually will show toggled between 0 and the high value. So we are wondering, is there any like filtering mechanism used? So we actually did like a black box study. So my student will try to turn on, will change the rate, how often we send a spoof message. And in the paper, there's a lot of detail. But surprisingly, one day my student come to my office and ask me, do you want to hear the good news first or bad news first? And then I know, well, what happened is that just by constantly sending good packet and stop, spoof packet stop, spoof packet stop, like in about 2 days, the tire pressure ECU just stopped working. So this is actually, I want to know what my tire just refused to show it, and I tried to reset my car battery, and I tried all sorts of things, and in the end, we have to ask for a dealer's help. And then we just stopped there because I really don't want to see dealer again. Okay, so actually there's, so we will see that there's not much security mechanism put in, and actually there's some very simple fix can fix problem. So if you see in this picture, you see all the tire pressure is normal, but still this warning light is on. So actually the TPMS only relied on one bit, the flag, to determine whether it should turn on this. Any human will know this is nonsense. So the first simple fix will be just add some cross-checking and also try to detect the conflict message. If there's 8 good message coming in, you should ignore the bad message. And if someone keep telling you there's a bad message, then you should feel suspicious. There's only supposed to be 1 message per 30 seconds. And of course, we can put on some like encryption algorithm, encryption to protect the sensor ID to prevent the car tracking happen. Well, there will be some like key management challenging, but those can all be worked out. And the other thing is that we should not only use one activation signal for the same brand. The activation signal itself should be protected. So, okay, let me conclude here. So in this study, we find out that for each TPMS message, it contained a sensor ID large enough to identify the car in US. And surprisingly, you can actually eavesdrop this message 40 meters away, and even the car is traveling at high speed. And for the spoofing risk, we show that there's actually no input validation. There's some weak filtering. Actually, this weak filtering not only not help, actually create problem. It disabled itself, permanently disabled in the end. The reason we conduct this research is try to raise awareness before more serious security or privacy vulnerability actually really show up. And we show that if you just be a little bit more careful and try to, you can actually, there's actually many mechanisms you can use to make the system a lot more safer. So that's all.
Hello, Kevin Fu, UMass Amherst. Question, what excuse did you give the dealer? And was your car still in warranty?
Well, let me say that I told the dealer, just reset the computer. I know the hardware must be fine. They said, we already did. You have to replace it. That's all I can tell you. Otherwise, they probably will ask me to pay for it.
Now, the sensors operate at like 400 megahertz, you said?
In most US sensor operate in 315 megahertz, and European car operate on 433 megahertz.
Yeah, that's like, you know, order meter wavelength. Have you considered using some sort of active antennas to try to like substantially extend the range of the attack? Because at those frequencies that should be practical. With most RFIDs, the frequencies are too, you know, the wavelength is too long, and you can't do that conveniently. But in that band, it should be possible.
Yeah, actually, I'm sure it's very possible. There's many technology you can increase the range. We actually just want to prove the concept, so we just paid $75 to buy this
The
thing.
cheapest antenna that was available.
Yeah.
So you said you oh, Ian. Ian Goldberg, University of Waterloo. You said you were transmitting on two 900 megahertz frequencies, and basically where the beat was a 300 megahertz frequency, and that's how you got to transmit. And this actually had never occurred to me before. It's probably occurred to lots of people, but so broadcasting on 900 megahertz, you don't need a license for. It's a free band. But broadcasting two 900 megahertz signals, suddenly you're broadcasting in a licensed spectrum. So do you need a license to do that or not?
Well, so actually, the real signal coming out is only on 315 megahertz. It's the signal you generated is, one is 900 megahertz, one is actually 900 and, I forgot the exact number, but the difference is 315 megahertz.
Right. So, but if you were to transmit on a 300 megahertz band, you'd need a license for that, technically. I'm just talking about legally.
Yeah, I get your point, but I think 315 megahertz probably is also unlicensed band. There's a few like slim chunks. 433 is also unlicensed, and some of 900 is unlicensed, and some of 800 is unlicensed.
Okay.
Brian Rosenberg, Qualcomm. I'm not sure what the regulatory situation is, but your whole 8 good sensor readings being overridden by the 1 bad one, that might be a requirement, right? You know, for sort of like safety reasons. If there's any reason to suspect anything's wrong, then you have to report that there's a problem.
Right, but the thing is, like, I am ECU. I'm literally asking you, are you fine? You tell me 8 times, I am fine, but maybe there's a weird sound coming out of nowhere. I say, no, he's not fine. And then I immediately believe that sound.
Yeah, I mean, I know it doesn't make sense, but sometimes the regulatory requirements don't, so.
Well, yeah, maybe.
Dan Wallach, Rice University. Have you contacted any of the auto manufacturers or parts suppliers and gotten responses or feedbacks, or you're an idiot, clearly we don't have a security problem, feedback from any of them?
We really want to don't do that, right? To tell people how stupid you are. But actually,
No,
we
they
did.
tell you.
I know. Oh, they tell me. Okay, that's possible. Anyway, so we actually talk with some car manufacturer, some researchers there. They actually give us some feedback, like the requirement of building this secure communication protocol. So, for instance, they will care more on how easy it would be if you add this key management and encryption things. If the dealer want to change the tire, if the user somehow wanted to change the tire, will this disable the whole TPMS? So they actually give us some useful input.